This is Saxon Advanced Math, Lesson 94B, and we're looking at graphs of the tangent and cotangent. So we've already gotten involved with sine and cosine, and then secant and cosecant. Now we're going to throw in tangent and cotangent. Now, I would suggest taking a few minutes to play with your calculator. And I know, or Desmos.com, that's another one that's really good. Desmos will let you set up your calculator in degrees, make sure your zoom is set out so that you get to negative 360 and positive 360 instead of negative 10 to positive 10, which is standard. If you did that, you're going to see a little tiny piece of the graph. You want to see a whole cycle at least. I would suggest playing with your calculator to get familiar with these. Now, this right here, the board looks crazy, and I realize that, and I've color-coded it, which is a scary thing for me because colors are a whole nother ball game. But I'm going to put it up here and see if we can just explore a little bit, and then we'll do some problems. Okay? First thing I want us to know is this is the y equals a tangent of theta graph. It does these little things like this. And if you think about that, there's a reason for it, because tangent has some undefined points. Those undefined points are when we're causing division by zero. See, that for a tangent, zero is fine, it's zero, but when I start getting into like 90, the tangent of 90, that's going to be an undefined term, or negative 90. And if you think about the triangle, it's because tangent is opposite over adjacent, and when the adjacent of the triangle in the unit circle gets down to zero, it causes the division by zero, and that causes an isotope. So we've got these isotopes occurring every so many degrees. Well, how many degrees are there? Well, that's between negative 90 and 90. So the period is every 180 degrees, we get one of these little swoops like this. Now, that's great, and that's wonderful, but what if we started to look at the cotangent? Let's compare those. The cotangent is very similar, but remember that cotangent is, instead of opposite over adjacent, it's adjacent over opposite. So it has different isotopes, and and that one is going to cause it to do these little swoops going down instead of going up. But it also causes different division by zero, because all of a sudden my division by zero for the cotangent, right, is going to cause these isotopes at zero, because at 0 degrees I would get division by zero, and I would get that division by zero again at 180. So it still has the same period, it just flips the direction and shifts the graph by 90 degrees. Well, that makes sense, right, as we start to look at this. Let's look at what happens if I throw a negative in here, and I've done the same thing. This is y equals the tangent of theta. There you can see it has the same isotopes. All I did was duplicate this graph down here for the tangent. But when we start saying that y equals the negative tangent, well, every positive value becomes negative, but the isotopes stay the same. So it takes this graph and just flips it, right? You see how that's flipping it over? And therefore the tails go the other direction, although the isotopes exist at exactly the same points. And that works for the cotangent and negative cotangent as well. Now, if you look at example 94.b, it asks, or 94.3, it asks, sketch the graph y equals negative 2 tangent of theta. Now, we're going to start dissecting this just like we normally would. The direction is negative, okay, so we're going to pay attention to that. There's a understood zero in here, which the understood zero means that my center line is going to be at 0. It doesn't change. Just like we did with the sine and the cosine function, we have no phase angle, right? There's no phase angle on this because this theta being added to or subtracted to 0. There's no number out front of there. That's good too, right? So this is a very easy one for us to work with. But when we start looking at it, we realize there's a negative. So if I graph this with the negative, right, it should look with a positive y equals tangent. It's going to flip that over. So y equals the negative 2 tangent theta. So I know it's going to be going down. If I just said y equals a negative tangent, it's this color right here that I put in, and that's what it looks like, right? But what is this 2 going to do it? And that's why I would suggest you play with your calculator, because until you start seeing it, it doesn't make sense to people, and that's understandable. When I throw that 2 in there, it flattens this out. It doesn't have as much of a swoop to it. That 2 means that the slope of the rate of the change is happening quicker, so it doesn't have as much time to slope. Notice it's more straight. It's almost like a straight line, almost like an angled line. It's not. There's a little bit of a curve to it, and it does get ever closer to the same isotopes, but it doesn't ever hit. the book didn't say to do this, but I wanted to see, I wanted you to be able to compare. What happens if it was a 0.5? And that actually makes this swoop more pronounced, right? It widens it out. So the smaller that number gets to, or closer that number gets to 0, the more that is going to turn this, going to be out further. And the bigger this number is, the more flat it is, which means that we could theorize if this was like a 5, it would be almost indistinguishable at this range for us to see it being anything but a straight line. So even though it isn't, this is the easiest way to do this, though, is that when you're sketching these, is to realize that you're just doing a sketch. Okay, so knowing which direction the tails go and knowing where the isotopes are, those are pretty much all the important things that you have to know. This right here, the 2, just means I'm going to draw it a little bit flatter. And don't feel bad as you sketch these, because I trace these. I cheat because on the trace to get it more perfect. If I was grading this or sketching this on a smaller piece of paper, of course I could sketch it from this, but my sketch is not going to be very perfect either. These are just sketches, and we're not looking for you to be able to define exactly where that point is on the graph. What we're looking for is that the tails are going the right way, the isotopes are in the right spot, and is it flatter or fatter? Right? Which way is it? And you would define that by this number is greater than greater than 1 or less than 1. And then which direction is by that negative. So we're not looking for perfection here, but we are looking for you to be able to identify the graphs. And to me, this is beautiful. It's a very cool looking thing that you can take these graphs, so these functions, find their inverses, right? Cotangent and tangent, and we can also work with their isotopes because their isotopes shift and change because of the division by 0. So I would suggest making yourself a little table and playing with this. Desmos does a really good job if you want to play with it online. It's free and will allow you to put in these parameters, but you'll have a deeper understanding of how the graph looks, and you'll be able to sketch these very simply.